The ELECTRO program interface consists of the menu bar on top, the message area and command line, the status bar on the bottom, the model tree and search on the left, and the model window in the center. When graphs are created, they are tabbed with the model window in the central area. To perform a simulation using ELECTRO, you must first construct a geometric model of the physical system. This can be done using the built-in geometric modeler or by importing geometry built using CAD packages. The sample model is an insulator imported using a step file. Select the step file import and choose the file shown in the video. On opening, a 3D insulator geometry is displayed, which includes a split ring and water droplets on the sheds. The latter features can only be modeled with 3D Coulomb software. Click on the Z=0 plane. ELECTRO will switch to 2D using the segments that exist on the Z=0 plane in the full geometry. An imported geometry summary appears in the message area. Units are set up from the model tree or from the utilities menu on top. Geometry objects are convenient for labeling and selection. This dialog can be opened by using the toolbar, the model tree, or the geometry menu. Left-click the Create button 4 times to create 4 generic objects. Right-click the objects and rename them as ground, high voltage, insulator, and ring. Click the Add Region button to assign appropriate regions in the model to the objects. By default, ELECTRO treats models as representing infinitely long structures. This model requires cylindrical coordinates. In the Geometry and Solution dialog box, switch the model type to axis-symmetric y-axis. In the electric settings, the Grounded Voltage Sources box is checked by default. Most models solved for electric fields should be set as grounded. Most physical equipment is grounded, and in those cases, solving as ungrounded would produce too high a field by the grounded electrode and too low a field at the high voltage electrode. To assign voltages to the different regions of the model, open the Uniform Voltage dialog box from the Physics menu or Model Tree. Enter voltages and use the plus button on the bottom to add regions to definitions. Position the mouse over regions and left-click. When the object appears green, right-click to end the selection. Click OK to close the dialog box. Note that in the model tree under Physics Applied in the model tree, when voltage of a region is clicked, that region will highlight orange in the model. You can edit it by right-clicking on the voltage label. To assign materials to the model, open the Material table from the Physics menu and assign copper to the ground, voltage, and ring objects. When all these objects are highlighted in green, right-click the mouse to end the selection. Similarly, assign glass to the insulator region. The model is now ready to solve. Pre-select outputs using the Define Output box under the Solution menu. Choose the Plots tab at the top of the dialog and click the Add Plot button to open the Plot Properties dialog box. Choose the 2D Graphs tab. Set the field quantity to electric field and location to a long segment. Select 3 segments on the high voltage region and right-click to end the selection. Since the field is discontinuous across these segments, the command line should prompt for a side to compute on. Left-click at a spot to the right of the selected segments to compute the field on the air side. The command line will prompt you for which direction to follow the selected segments, while arrows appear on the segments to display the active direction. Left-click to accept the shown direction for the plot. The interface will return to showing the Define Output dialog, but with one defined plot. Following a similar procedure, click the Add Plot button, then select the 2D Contours tab. Define a voltage contours plot on a plane. Similarly, define an electric field arrow plot on the same plane. Select the Measurements tab and click the Add Field Probe button. In the dialog, select E field as the field quantity and X, YI coordinates as shown. Now all the outputs are defined. Close the dialog. From the Solution menu, select Run Solver. When the solver is finished, the Output Manager box will appear. To see the plots, click the Show Step button. To customize the presentation of the plot, right-click on the label and select Properties from the pop-up menu. This enables the plot editor for the selected plot. Select the 2D Graphs tab and click the Show Step button to display the graph. This graph shows some rather sharp features and a big gap between the dots when transitioning from segment to segment. This is not expected for geometry with continuous derivatives. We can improve the solution with local refinement. There are many ways to accomplish this with ELECTRO. For example, if you would like to improve the whole solution, Refine Solution is the best method. Since we are interested in a local area, we will tell ELECTRO to put more weight on the solution quality in this area. Run the solver again with the new weight selection. The outputs now have 2 steps. The original graph and plot are still available in Step 1. The new graph and plot are in Step 2. Delete the first solutions graph to better focus on the second improved solution. Right-click on the graph curve and select Trace. The curve highlights corresponding geometry in orange in the model window, and a blue dot indicates the current trace point. You can now easily identify where plot features occur in the geometry by moving the mouse across the graph. This sample session has introduced basic techniques that you can use to perform ELECTRO simulations when beginning with a CAD model.